The plane touches down. In that exact moment, those tires go from a dead stop to over 170 miles per hour in less than 1 second. And they're not just spinning up. They're taking the full weight of a 400,000-pound aircraft, slamming into asphalt at nearly 200 feet per second. 6 tires. That's it. And not one of them explodes. Every single time. The question isn't whether they hold. It's how. And the answer involves a gas that isn't air, a material used in bulletproof vests, and a small component specifically engineered to destroy itself before the tire can blow. Let's start with what actually happens in that first half second of contact, because most people have no idea how violent it is. When you watch landing footage in slow motion, you can see the tire deform, the rubber squashes, the sidewall bulges. That's not a flaw. That's the tire doing its job. But in the same instant that deformation is happening, the rubber on the contact patch goes from 0 rotation to full runway speed. There's no gradual acceleration. It's instantaneous spin-up, and the friction generated in that moment is enough to vaporize the surface of the rubber. That smoke you see puffing up when a plane lands? That's not the brakes. That's rubber burning off the tire. A commercial aircraft tire loses a measurable amount of material on every single landing. Not enough to matter structurally, but enough to leave a black smear on the runway and a cloud of smoke that you can see from a mile away. Now here's where the numbers get hard to believe. A typical main landing gear tire on a Boeing 767 operates at around 200 pounds per square inch. For reference, your car tire runs at about 32. We're talking roughly 6 times the pressure. And that pressure is sitting inside a tire that may be absorbing the impact of 150 tons of aircraft. The peak load on a single tire during a hard landing can exceed 50,000 pounds. That's the weight of a loaded semi-truck, concentrated on a contact patch roughly the size of a large pizza. So why doesn't it explode? The first answer most people give is that airplane tires are just really thick and strong. And that's not wrong, but it's the least interesting part of the story. The real answer starts with what's inside. Here's something that surprises almost everyone. Airplane tires are not inflated with air. They're filled with nitrogen. And before you think, that's just an aviation quirk, understand that it's not a preference. It's a requirement. And the reason tells you something important about how engineers think about failure. Regular air, the stuff coming out of a compressor at any airport, is roughly 78% nitrogen, 21% oxygen, and a small amount of water vapor. That water vapor is the problem. At 200 psi, and the temperatures generated during landing and braking, moisture behaves unpredictably. It expands, it contracts, it can accelerate oxidation inside the tire structure, and, in the worst case, it can contribute to pressure spikes that would never happen with dry gas. Nitrogen is inert. It's dry. It doesn't support combustion. And critically, it behaves predictably across a much wider range of temperatures. If a tire gets hot, and they do get extremely hot during braking sequences, nitrogen pressure increases in a linear, calculable way. You can model it. You can engineer around it. Moisture-laden air introduces variables that no engineer wants near a loaded landing gear at 200 knots. I'll be direct about something here. I think the aviation industry undersells this decision. You'll find articles that describe nitrogen as a better alternative to air, as if it's an upgrade. It isn't. Nitrogen isn't the upgrade. Air was always the wrong choice for this application. The physics of high pressure, high temperature containment with a reactive gas mixture simply don't work. Nitrogen isn't better. Nitrogen is correct. But even with nitrogen, the tire still has to physically contain that pressure through impacts that would destroy most structures. And that's where the construction gets genuinely impressive. I spent part of an afternoon once at a maintenance facility, watching a tire being prepped for inspection. Not the most glamorous afternoon, but the kind of thing that sticks with you. What struck me wasn't the size of the tire, though they are enormous up close. It was the weight. A main gear tire from a wide-body aircraft weighs over 100 pounds. You don't throw it around. And when the technician explained what was inside, it reframed everything I thought I knew about tires. An aircraft tire is not, in any meaningful sense, just a rubber tire. The rubber is almost secondary. What you're actually looking at is a composite pressure vessel, a precisely engineered layered structure where rubber is the matrix, and high-strength textile is the load-bearing element. Specifically, aramid fiber, the same family of materials used in Kevlar. Woven into cords, oriented in precise angles, layered in a sequence that distributes stress in 3 dimensions simultaneously. There can be 30 or more of these plies in a radial aircraft tire, each one adding tensile strength without adding the brittleness you'd get from a purely rigid structure. The genius of this design is that it's simultaneously rigid and compliant. Rigid enough to hold 200 psi, compliant enough to deform on impact and then spring back. That combination is extraordinarily difficult to engineer, and it's why aircraft tire manufacturing is dominated by 2 or 3 companies globally. It's not a commodity product, it's a precision component. And yet, even with all of that, even with nitrogen, even with 30-plus plies of aramid, there's still a scenario where the tire can fail. And when engineers designed for that failure, they came up with something that I think is one of the most underappreciated pieces of engineering on a commercial aircraft. It's called a fuse plug. Every aircraft tire has them. They're small alloy inserts embedded in the wheel rim, positioned around the circumference. Each one contains a material with a precisely calibrated melting point. And here's the function. If the tire temperature reaches a threshold that indicates imminent structural failure, typically caused by prolonged braking or a brake that's seized, the fuse plug melts. The tire deflates. Quickly, but in a controlled way, through a small orifice rather than a catastrophic blowout. This is the part that most explanations of aircraft tires skip entirely, and I think it's the most important part of the whole system. An explosive tire failure on a landing gear can throw debris with enough force to penetrate fuel tanks, hydraulic lines, or adjacent structure. There are accidents in the historical record where this exact sequence happened. The fuse plug exists to make that scenario essentially impossible. Instead of an unpredictable explosion, driven by heat and pressure, you get a controlled deflation that the pilots may not even notice immediately. The aircraft stays on the ground. The gear stays intact. The runway surface doesn't get peppered with shrapnel. What I find remarkable about the fuse plug isn't the technology. The technology is simple. It's a plug of metal that melts at a specific temperature. What's remarkable is the philosophy behind it. The engineers didn't design a tire that couldn't fail. They designed a tire that fails in the most controlled, survivable way possible. And that distinction between preventing failure and controlling it runs through every good piece of safety-critical engineering I've ever looked at. The fuse plug melts before the tire can build enough pressure to rupture. The tire deflates before a catastrophic failure can cascade into a structural event. Every step in the failure chain has a designed-in interruption. That's not luck. That's decades of accident investigation turned into mandatory design requirements. Now, here's the last piece, and it's the one that genuinely surprised me when I first encountered it. After all that engineering, after the nitrogen and the aramid and the fuse plugs, you might expect that an aircraft tire is a single-use component. Something so precisely built, subjected to such extreme loads, surely it gets replaced after every flight. It doesn't. A typical commercial aircraft tire is certified for several hundred landings before it's pulled for inspection. And when it's pulled, unless it's been damaged, it's not scrapped, it's retreaded. The worn tread is buffed off. New rubber is bonded to the carcass. It's cured, it's tested, and it goes back into service. An aircraft tire can be retreaded up to 6 or 7 times over its service life. The same structural carcass, the same aramid plies, the same engineered composite, making hundreds of landings across multiple retread cycles before it's finally retired. Compare that to the automotive world, where retreaded tires are treated with skepticism, where the idea of using a retreaded tire on a performance vehicle would make most people uncomfortable. The aviation industry has been retreading tires since the 1940s, under certification standards that are more rigorous than most new tire manufacturing processes in other industries. They don't retread because it's cheap. They retread because the carcass is the expensive, precision-engineered part, and replacing it when the tread wears out would be wasteful engineering. Aviation figured out something that the rest of the tire industry still hasn't fully internalized. The structure and the wear surface are two separate problems, and you should design for both independently. That's the system. Nitrogen for predictable pressure behavior. Aramid composite construction for load capacity with compliance. Fuse plugs for controlled failure. And retreading because the engineered structure is too valuable to discard along with the tread. None of it is an accident. None of it was obvious. Every element came from someone asking what happens when this goes wrong, and then engineering an answer. The next time you feel that thump on landing, that's what's absorbing the hit. 100-pound pressure vessel full of inert gas, wrapped in textile stronger than steel by weight, equipped with a safety valve calibrated to save the aircraft before the tire can destroy itself. And when it wears out, they peel the rubber off and do it again. If you've watched this far, and you're still curious, there's another video on screen right now about something you walk past every day and have never actually thought about. Click it, and if you want more of this, subscribe. New video every week.